Hello everyone, and welcome to today's webinar. Today we're going to be presenting a short introduction to Ethernet for control engineers. The purpose of this webinar really is to acquaint someone who is not familiar yet with Ethernet but is moving in their industrial automation environment to a Ethernet type of application. Specifically, we'll talk a little bit about industrial Ethernet, but mainly we want to set the tone for Ethernet in general. Sponsors for today's webinar include these members of PTO. We'd like to thank them for contributing our ability to do this for you today. My name's Carl Henning. I'm the Deputy Director of PTO. PTO is the nonprofit member-supported organization that educates North America about Profibus and Profinet. I also blog at profiblog.com. You can also follow me on Twitter. The main presenter today is Hunter Harrington. Hunter is a Profinet consulting engineer with the Profi Interface Center, or PIC as we call them for short. The PIC is the certified Profinet Competence Center, test lab, and training facility for North America. Here's our agenda for today. I'm going to give you just a one-slide overview of the organization behind Profinet. We'll talk then about Ethernet for control engineers, talk about what Ethernet is, why we use it in the industrial space. We'll look at the famous 7-layer OSI ISO model and how that applies to network communications, specifically Ethernet. We'll look at the standards that the technologies are based on, look at the differences between Ethernet and industrial Ethernet, and then finally get into some detailed networking basics. We'll follow that up with resources that you can go to for additional information beyond what we talk about today. And we'll conclude with the question and answer session. You can answer your questions at any time in the question and answer frame on the right-hand side of your screen. The organization behind Profinet is called PI, which is short for Profibus and Profinet International. I'm not going to read you all of the great numbers and information off of this slide. The thing I do want to point out to you, though, is that there is global support available for this technology. Just about anywhere in the world you go, you will find a competence center that can talk about Profinet and Profibus. Also, I wanted to draw your attention to the fact that from a market share standpoint, globally, Profinet, Ethernet IP, and other have equal market shares. With that, I'm going to turn this over to Hunter Harrington and let Hunter get us into detail on Ethernet for control engineers. So, Hunter, over to you.
Thank you, Carl, and welcome everyone to today's webinar on Ethernet Basics for Control Engineers from my side. I just want to quickly go over the agenda today, what we're going to cover a little bit more detail. We're going to first talk about Ethernet, what it is, and why we would want to use Ethernet in the industrial field. We want to talk about the OSI ISO model and how that applies to network communications, because we can't really talk about communications without that model. Then we want to talk about the standards themselves, Ethernet, IP, TCP, UDP, and so on. Then we want to talk about, we often get the question, what's the difference between Ethernet and industrial Ethernet? So we want to clear that up. Then we want to go into more networking basics. So we want to cover an overview of networking components, switching technology and full duplex, switch features, network messages and types of messages, routing and subnets, topologies, and then we'll conclude with discussion about network addressing and naming. So first off, let's talk about Ethernet, what it is and why. What is Ethernet? Of course, Ethernet's been around for many years. It actually came about in the 1970s. It was research at the Palo Alto Research Center came up with Ethernet, and in the original design, and it's used to transmit a signal between two or more devices over a shared medium. Of course, the original Ethernet, you could have all the devices were on the same network and they were shared. They shared the same cable. You maybe had some rules where you had to have a terminator and so on. You can see from the original drawing here. That's kind of changed today. We have the carrier sense multiple access collision concept for those shared networks, but that's kind of changed today what we're going to talk about today, typically we use Ethernet over a switched medium, so you're using Ethernet switches, and we'll talk about how that works. You also notice as Ethernet has progressed over the years, we started with a 10 megabit per second Ethernet. We then went up to 100 megabit per second Ethernet, fast Ethernet, and then now we're up to gigabit and even more than that being researched currently. The Ethernet standard is known as IEEE 802.3. It was developed by the Institute of Electrical and Electronics Engineers, and it's now been adopted as an ISO standard, which means it's a worldwide standard. It's actually become the most popular and widely used networking technology in the world. Due to the advances, really, and the advances of Ethernet gives us now the capability where we could not really use it very well on the factory floor in the past. Now, due to the advances of Ethernet, it's taken, of course, many years, from the 1970s to today. We're looking roughly at 40 years there, but we've brought it out down now to the field device level. Because of the advances of fast Ethernet, IEEE 802.3u means we can talk at a 100 megabit per second rate, and that equates roughly to 12 megabytes per second. We also have full duplex capability. What this means is we can use an IEEE 802.3x mechanism where the devices on the network can send and receive in both directions at the same time. And finally, due to the updates of the switching technology, switches provide full duplex links, and this means that you don't have the collision issue you might have had in the early Ethernet days, because those collisions could cause delay or problems on the network. And with the switches, we don't have to worry about that anymore, because the switches basically give us a point-to-point link between the devices. This results in a much higher bandwidth and reduces delays on the network. And it also ensures that the messages, previously the messages on the shared network went to all devices, but when we use the switched network, the message only goes to the device that it's intended to go to. The reasons we build on Ethernet, of course, is because it is a worldwide standard. We can leverage the current research ongoing with the IEEE organization and the improvements of Ethernet. It's also an open network, so many protocols can run over that system. We can even integrate it into our enterprise, our office facility, or our environment where we can maybe bring data from the shop floor up. We can even use IT tools, standard IT communications, to read information from the devices to find out things. It's also a future-proof system, highly scalable, and we do then gain in the performance contrary to the other field buses. The earlier field buses may have run at a slower speed, maybe like 1 megabit or something, depending on what field bus you're talking about, but the bandwidth has greatly increased, so now we can transmit more data over the network. So now that you know about Ethernet, let's now talk about the OSI ISO model and talk about how it applies to network communications. Again, we can't talk about networking without talking about this model, and it's kind of confusing, the name they gave, I know. It stands for International Standards Organization Open Systems Interconnect Model. It's a 7-layer model where each communication procedure is divided into logical components, which are linked via these defined interfaces. So if you look on the left-hand side here, we have maybe a device or a computer on the network. We have the 7-layer model, and kind of remember from college I learned an acronym that all people seem to need: data processing. And that's kind of an acronym maybe you can use to remember this, but we start off with the application layer, the presentation layer, and the session layer. These are known as the application-oriented layers. So you have a protocol or an application you want to run over the network. The service, maybe you want to have a web service or web application. You can design that application, then you have to tell how you want that information to be formatted or coded, and how you want to synchronize or control the communications for that application. That would fall up here in these layers. Then if we actually want to talk about the network or how we want to transport that information across the network, we now can talk about layers 4, 3, 2, and 1, where we have layer 4 is the transport layer, TCP or UDP if you've heard those terms. We're going to talk about that lets us link the devices together, maybe have a connection. Then we have layer 3, the network layer, or the internet layer. This is where we can actually assemble packets or datagrams, route that through a network. And then finally, at the lower two layers, we actually have Ethernet. So layer 1 and layer 2 are the Ethernet layers, whereas layer 1 is the physical layer. Layer 2 is the data link layer, where you actually have the Ethernet frame, and you send that Ethernet frame across the network. Now, the ISO model for most applications is kind of a little bit too complicated, maybe, so they decided to remove the 5th and 6th layer, and we created a model for the Internet we call the Internet or TCP/IP model. And with this model, we now map the application layer, again layer 7 to the top, and we take layers 4, 3, 2, and 1 in that layer. So we reduce some of the complexity of that. And now we have the Ethernet level at the, and when we talk about Ethernet, we typically talk about the MAC address. This is where you're sending the addresses, and we'll talk more about the addresses too. We have IP, or the network layer becomes the Internet layer or IP layer. We have an IP address there. Then we have the transport layer or TCP/UDP layer, and at that layer we talk either TCP/IP or UDP/IP, and then we have an address like what's called a port number, and the port number represents what port we want to use, maybe if we want to talk to a particular application. For example, port 80 would be the port if we were wanting to talk to an HTTP server on the Internet, for example, a web server. The main thing to note about this slide, and we want to make sure you understand, is over Ethernet, multiple application protocols can run at the same time. And this shows kind of the concept where we're applying the OSI model communications, where we do have multiple protocols running on a PLC or a computer, this could represent. And now we're talking through the web, we're talking through our maybe our network server, we're talking maybe some socket communications, and then maybe we're talking industrial protocol like Profinet. And with that, we're able then to support many different applications on a device or a computer and use this model to support multiple application protocols and devices. To show you again how that kind of works from a communications perspective, if you have, for example, let's say we use a TCP/IP protocol, and TCP/IP uses a client-server model. So if we decide to do that, we have to now map those different layers of the TCP or Internet model, in this case, to some data. And we're going to show how we can take that data here in a minute and how we would put it into a frame to send out over the Ethernet network. And you can see as we step through, we have to now package this data in the message we're going to talk about. So now let's talk about the standards. We're going to talk about Ethernet, the Internet protocol, TCP protocol, and UDP protocol. And a lot of times you hear people say the term TCP/IP or UDP/IP. The main thing I want you to know again is that those are really different things we want to talk about. As we go through the standards section, we want you to know that there's IEEE standards and there's RFC or Internet standards. The IEEE standards can be found at www.ieee.org. Examples of that would be the Ethernet standards or the wireless LAN standards. You also can find the Internet standards like TCP, IP, or UDP if you go to the RFC sites or to the Internet Engineering Task Force website at www.ietf.org. Just keep in mind, if you do go to those sites and start looking at the standards, which we name, a lot of times those specs or RFCs might have other documents associated with them, or other where you might have to delve deeper to find what you're actually looking for. Let's first look at the IEEE 802.3 frame. So the Ethernet frame consists of first of all, a preamble and SFD or start frame delimiter. Then you have a destination MAC address of where you're going to send the data to, a source MAC address of where that data is coming from. Then the Ethernet frame has a field called an ether type field, which is important for us to know because this field tells the receiver of this Ethernet frame what type of data is going to be inside the Ethernet frame. So let's say we have an ether type of 800. That might indicate that there's some further Internet data inside of this Ethernet frame, for instance. And inside of the Ethernet data portion of the frame, we can have roughly from 46 to 1,500 bytes of data. Each Ethernet frame has a frame checksum, or a CRC calculation that's sent from the sender to the receiver. That way they can check to see if that frame is still good. And if the frame is good, the frame will be processed. If the frame is bad, the frame will be dropped or thrown away. And remember, MAC stands for Media Access Control. This is typically the physical address we use when we're actually talking over the Ethernet network. You have to talk from one MAC address to another MAC address when you're talking over Ethernet. Let's talk about that encapsulation so we can understand, again, how this is fitting into the communication model. So if we have some data we want to send, let's say some user data we want to send over the network, we first have to package that data with some application information. So we have to say, what application is this data coming from? Maybe, again, it's an HTTP application. Then if we want to send that data using TCP/IP, or TCP, excuse me, first, then we need to maybe establish a connection, and now we need to put a TCP header on that data, and we can then use the transport layer to send some of that information. If we want to now send that over the internet, we now have to add an IP header to that message to say this is some internet protocol information in here as well. And finally, if we want to send that over the Ethernet network, we have to add the Ethernet header and trailer, and that basically builds our Ethernet frame. And those other headers, the IP header, TCP header, and the application data, are all going to be put inside of the Ethernet data. So the main thing we want you to realize here is the more layers you use with your protocol, it indicates more overhead and more processing that needs to be done on the sender, for instance, or the receiver to unpackage that message or package that message up. So when we look at protocols on the network, if we want faster protocols, we sometimes might want to look to see if we can bypass some of that stuff, if we need to look for a faster protocol, or if we want to use TCP/IP, then of course we would need to use it this way. But it depends on your application, and we'll talk about that again, how different applications do that. We show an IT comparison here in just a minute. The Internet Protocol, or RFC 791, now we're up at the Internet layer, layer 3. This protocol provides best ever delivery of datagrams through the network. It is a connectionless protocol, however, so you don't actually establish a connection with the receiver of this message. But it does give us a way to do a hardware-independent addressing system, so logical addressing. So probably most of you have seen a regular 32-bit IP address, for example, 211.154.184.16. That's a regular version 4 IP address. Now they have a new version 6, but we won't get into that address. It's pretty long. But we can now, on each computer or device on our network, assign an IP address, and now we can use that IP address to route between other networks based upon the IP address and the network identification in that IP address, or we can use different IP addresses on our local area network and then basically keep track of the devices using the IP addresses. Because if we decide to use TCP/IP or UDP/IP or IP protocols like IGMP or ICMP, then we can now send more than 1,500 bytes of information. We saw that in the standard Ethernet frame, we could only send roughly 1,500 bytes. Well, what happens if we have a 2 megabyte file or an email we want to send to a colleague? Well, that file now needs to be chopped up into chunks, and it needs to be fragmented and then sent to the receiver, and then on the other end it can be reassembled. And that's what IP gives us. It allows us to build these datagrams, fragments, and then put them back together on the other end. But however, keep in mind it is connectionless. What TCP does is, and UDP, first of all, TCP or RFC 793 now allows us to do a connection. So we can create a connection to that partner, and we can follow a client-server principle. But keep in mind that the client-server principle is half duplex. So we have to say, server, here's some data for you. Can you process this data? Now the server says, yes, I can. Here's what I need to do, and he lets you know. It is built for reliability. TCP, and it provides you error control and flow control. And now we could send a group of TCP/IP messages to a partner, and we know that those messages are going to be sent to that partner, and they're going to be acknowledged and received by that partner. He's going to get all those. If he doesn't get all those messages, he's going to let us know with the error control. He'll say, hey, I didn't get part of this message. Can you resend that message? Then the TCP protocol would allow us to resend that message. But keep in mind, it is going to be there's going to be some delay with TCP. TCP was invented for the office world to use on the internet and to use in the cases of where you might need that error control or send a lot of data to another recipient. Maybe you're sending, again, a gigabyte file now. Well, you want to make sure that whole file gets transferred correctly, and that's what TCP will let us do. Another protocol at the layer 4, we're now at layer 4, is user datagram protocol. UDP, or RFC 768, is now still a connectionless protocol similar to IP, and it's built more for speed. So it's similar to you send a message out, but you don't know, again, if that message got received by the partner. And again, let's talk a little bit more in detail about both of those. TCP is, again, layer 4. It's connection-oriented, uses an end-to-end connection with a three-way handshake. So you have to go request to the server, you want to open a connection. The server says, yes, that's fine. It'll respond to you. Then you can talk to the server, send your data up to the server. You can send multiple messages in a sequence, and that message could be resequenced if it needed to, if it came in out of order on the server. That's one of the features of TCP. There's flow control, and there's graceful close. The main thing about TCP is it uses addresses an application via a port number. So again, if we were talking about a web server, a lot of times you would use the port number 80, and you would send to that web server over port 80. Or if you're sending an email to a colleague, you would, for example, use port 25 in the background and uses that port to send the data to the email server. Okay, UDP, again, is connectionless. Again, it might be used for an example application like video conferencing, or if you ever used a chat client like on the internet, a lot of times like Skype or something like this, you would be using UDP/IP, and what it does is it sends the messages with no confirmation of the message being sent. So in that case, you might see, for example, on a video screen, you might be sending data to that video screen, and maybe you see the video screen flicker or something happen on the video screen. It could have been that a message was missed or didn't make it. In that case, you're still able to see the overall image of the video screen, and you see what's happening. Or, for example, again, with a chat client, you're talking to a colleague over your chat, and let's say the message drops out for just a second in the middle of what you were saying. Well, then, since you're talking to an actual human person, they could tell you, hey, I didn't hear what you said. And then you could then start talking to them again, and then they would get the message. So the advantage of UDP, of course, is it uses less protocol overhead, and it uses addresses and applications still via a port number. But again, the disadvantage, I guess, of it is you don't know if the message always makes it there. Okay, let's look at some IT applications at layer 7 of the model. And if we look at some of the different applications that are used, I just want you to realize that depending on the different protocols that we have or different applications, they use oftentimes different transport layers. You remember we talked about the transport layers, layers 1 through 4. So for example, the ARP protocol and the RARP protocol, they just work over standard Ethernet. And I still remember from the old days when I used to work with Novell Networks, the IPX SPX protocol also worked over Ethernet. Other protocols, for example, ping, use the IP layer. And then we have other applications, for example, FTP or HTTP. They use the TCP layer. And then TFTP, so someone decided they wanted to make instead of a file transfer protocol server, they wanted to make a trivial file transfer protocol server. In this case, they decided, well, let's just use UDP for that, make it faster. And then we also could have maybe some diagnostics, like SNMP diagnostics, so we could also use UDP for that. It depends, again, based on the application you want to use and how you want to apply that to the model on maybe what transport layers you want to use. And we have an explanation there of all the different protocols we've defined there. Again, FTP is file transfer protocol. HTTP is hypertext transfer protocol for web services. TFTP, trivial file transfer protocol, and SNMP, simple network management protocol. These also might be interesting if you're actually using the Ethernet and industrial applications out in the factory, because you can actually take advantage of a lot of these protocols and use them in the industrial field. Okay, let's talk about the differences between Ethernet and industrial Ethernet real quick. What is industrial Ethernet? What does it mean when someone says, I've got industrial Ethernet? It basically means that it's a standard IEEE 802.3. We don't change anything with the 802.3. It's only now that we've given the device or the product a more industrialized design. So because we know in the factory, there's a lot of different environmental conditions or concerns, and maybe even functional concerns we're going to talk about. So we might have to look at higher temperature ranges on the device, and more rugged housing, maybe a more rack mount design, fanless products so we can withstand vibration, even industrial connectors and cables, and of course more noise immunity, and maybe even redundancy for a functional perspective. Because again, the office environment and the industrial environment are a lot different. In the office, it's air conditioned. You have usually some IT staff guys that know what's going on there. If they need to run a new cable, they can go up in the ceiling and run the new cable through the ceiling. The availability of the network's not as high, so second-to-minute ranges are accepted. Of course, we probably all know when we put in the IT ticket, sometimes we might have to wait a while to get the problem fixed. So it's not as critical. And the device density, a lot of times you have bigger switches, and those switches have maybe 24 ports or even more that they bring these cables back to. The topology a lot of times in an office environment is going to be a star. But in an industrial environment, we're usually talking about a lot more rough environment, and we need to have some commissioning personnel out there that know how to work with that particular system. And the topology a lot of times might be plant specific. We might need a redundant type of network, or we might need a line or a more linear type of topology than a star, because maybe that's the way the machine's laid out. And the network downtimes in the factory need to be a lot less, so maybe even less than 300 milliseconds, because we don't want to have parts falling in the floor or problems existing out there for long periods of time, because then we know that means that we're not able to produce the products we need to do. Also, the device density, for example, the switches, a lot of times you don't need so many ports on the switches, so 2 or 4 port devices are now available where you can actually have the devices have a switch built into the device, and that way you're not always having to run a star topology back, because we know that gets into a lot more cabling and a lot more network drops that you would need to worry about then. And of course, network monitoring is important, because we want to keep track of the network, be able to monitor how the plant's running. In automation, we also can use commercial off-the-shelf switches, but the question is, will they work in the industrial environment? And I remember Carl blogged about this too. If you bought a switch at Best Buy, would it work? Well, it might for a while, but we recommend you look at industrial switches for factory use, because they're a lot more rugged and have higher temperature ratings rated for that environment and are tested more to industrial specifications. Because again, we have the difference in the environment that we have to consider as well. Whereas in the office area, there's no moisture much, there's no high temperatures, no vibrations, and low noise and low dangers to mechanical or radiation and things like that. Whereas in the field, we have usually high temperatures, extreme, maybe even some areas. We have high dust. We have probably moisture in the plant from coolants or whatever we might have out there that's coming off the machines. Vibrating, machines. We have high noise probably. We maybe have some high frequency drives or something we're running on the network with some pretty heavy-duty motors, and those kinds of things can induce noise maybe even into the system, so we have to be careful. We probably also have moving things. We have danger of something getting damaged, maybe if something hits it, so we need to be careful. Also, the cabling and the things we need to care about, because we probably have some chemicals floating around out there that we could get on the cable, the Ethernet cable, so we need to think about those types of things. Now let's talk about some networking basics And first of all, I want to start off talking about an overview of network components. There's many types of connectivity devices we can use on a network today, and they all help to manage traffic on the network. A lot of these devices will help us with connectivity, maybe addressing, signal regeneration, filtering, or maybe even protocol mapping if we're wanting to map between different protocols. And again, some of these devices are a hub, or what we would call a multi-port repeater, switches, and routers, and a layer 3 switch, firewalls, and gateway. And now the latter three there, we probably won't get into too much detail in today's webinar, but we want to mainly focus on hubs, switches, and routers. What do they do? And if you want to learn more about the other three, you can look into our other more extensive webinars. Okay, so first of all, from an OSI model viewpoint, the network components, a hub or repeater will be at layer 1, and all it really does is repeat the signal that it receives out of all of its other ports, and that's what the hub does. It's kind of a multi-port repeater. Switch is actually really the birthplace of where we could actually now start using the field devices on Ethernet, because what a switch does is I'll talk about that again in more detail, but it uses the MAC address to send the information to the destination. Routers will let us connect different networks together, and they use the IP address for that. So we can have a device on one network, let's say network A, and it could talk to a device on network B by using routing and the IP address. And then also, if we wanted to talk between applications, we could use a gateway for that. We could have a gateway translate one application protocol on device A to talk to another application protocol on device B. So what are hubs? Hubs, and the reason we say no more, is were originally used with Ethernet, but they have a lot of issues now in today's network, so we probably don't want to have to deal with. First of all, it causes the network to function as if we're connected by a single line. So all devices on the network will send the device which sends a message that message will be received by all other devices, whether they need that information or not. So again, it's a multi-port repeater, and it results in a higher network load. So we don't recommend that in field level installations because of that, because it's going to cause that loading. And also, the hub often will work half duplex. So it means now you're back to the old style Ethernet where you can have collisions occur on the network, and those collisions, so if you have device, the first device and the last device starts talking at the same time and they conflict, have a collision, then you have a random back-off time, so there's a delay that occurs then on the network. So really, again, where we're going to go now is we want to talk about switching technology and full duplex, and this is really what we need when we're talking about factory floor Ethernet. Because switching technology, what it allows us to do now is it allows us to have multiple devices on the network, and those devices have full duplex links, so we don't have any collisions. Also, we have switches, we can handle multiple speeds. So you could have 100 megabit per second devices out there, and then you could use gigabit for your network backbone. And a switch allows us to have a point-to-point link between devices. So you can see in the picture, A is talking to C, while B is talking to D, and that's happening simultaneously. And the switch is intelligently forwarding those messages using the MAC addresses of those devices to the intended recipient. And that's happening in US, or microseconds, excuse me. That's happening in, that's the term for microseconds. So that's really fast timing when you're using switches. So the problems that we had before where the network was becoming loaded is greatly decreased when we use switches. So we have that increased performance now. And again, that's because we use full duplex. So you can have transmission of the data in both directions simultaneously. Now let's talk a little bit more about switch features. So what industrial switch features are available? As you can see on the left-hand side, there's many different features available, and we wanted to talk about these features so you would know what they are when you actually look at the switches and you're maybe picking a switch to use for your industrial plant. The first feature you probably want to look for again is that 100 megabit full duplex, and that comes with most all switches today you would get. It'd be very rare that you wouldn't have that on a switch. The other feature you probably want to look at is to make sure that switch supports auto crossing or auto negotiation we're going to talk about. Also, when you're looking at switches, you may hear the term managed switch or unmanaged switch, and the managed switches often offer more advanced features. Also, switches might have a quality of service or priority they can use, and this will allow us to prioritize frames according to another IEEE mechanism called 802.1PQ, which allows us to prioritize and put a priority in the Ethernet message, and then the switch can look at that priority and send that message faster or bypass the messages. There's also a couple more here we're not going to get into a lot of detail about today, but link aggregation allows you to increase bandwidth. Port mirroring is another nice feature if you want to monitor traffic of a device. And then VLANs are if you want to isolate traffic on your network to maybe different virtual LANs or different network sections. So first, auto crossover. Normally in the past, when you had two switches connected like we see in the picture there, you can see that if you didn't have the crossover cable, you'd have two transmitters transmitting to each other and two receivers listening to each other. Of course, that wouldn't work. So you have to have a crossover cable in order to have the transmitter on the left-hand side switch talk to the receiver on the right-hand side switch and vice versa. And in the past, that was always a problem because we would have a guy out there and he wouldn't know what kind of cable he had, and maybe he needed a crossover cable or not. Well, he could have the issue, and it took him a while to figure out, hey, I need this kind of cable. And so what we decided to do, and on a lot of the newer network components, there's a feature called auto crossover. And what that means is you can use a standard straight Ethernet cable, and then the switch will automatically cross that over internally. So it'll let the transmitter then talk to the correct receiver on the other side, and vice versa again. Auto-negotiation. Auto-negotiate is a way for switches and devices to automatically figure out the speed of the network and the duplex, whether it's half or full duplex or if the speed's 10, 100, or 1,000. And so when the switch comes up or the device, they'll query each other and kind of ask what's your speed duplex and figure that out in the background, and then they will automatically negotiate that speed and duplex. Now, one note, if you disable auto-negotiate on the device or network component, be sure to realize that will default that device to the 10 megabit half duplex, part of the standard. Okay, switches managed versus unmanaged again. Managed switches are plug and play, but they also support other features like diagnostics, SNMP, or advanced features so you can access the switch via the web page, or maybe you can commission the switch or configure the switch, maybe if you've got a redundant network. It can also help you diagnose issues. There may be a little bit more cost to a managed switch, but a lot of times we recommend you use those so you can have that additional diagnostics. If you get unmanaged switches, they're plug and play, but they usually do not have many additional features. So what you see with those switches is what you get. So you just plug them in and they go, but if something happens, the only diagnostics you have are the LEDs on the front of the switch. So if there's a light on and it's still green, but the network's not working, then that might still be maybe the switches went bad. You don't know those types of things then, so it's harder to diagnose if there's a network problem. Okay, quality of service, the priority field. So let's first talk about the IEEE 802.1p enables traffic priority, or what we call QoS, quality of service, on layer 2 switches, and we can do that if we use the Ethernet and the priority tag, or VLAN tag. Without QoS, the switch will basically forward the data in the order it receives it. So first in, first out. So if we had A, B, and C sending data to D, and it came in A, B, C, then of course it's going to go out that way. A is going to go to D, then B, and then C. Let's say that C is actually the high priority message we want to get through. So we've added a priority field now in the Ethernet frame, and we've marked that priority higher than standard TCP/IP. Now the switch understands that, it now will get those messages. It supports QoS, so now it knows to forward C first, and then the next one. So it's a way to prioritize the more important traffic on the network. And a lot of protocols support that. The more maybe higher priority protocols will support having that priority flag set. Okay, let's talk about the types of network messages we can have. First of all, the types of messages we can have on a network. You can have a unicast message, where that message is sent to a single recipient. You can have a multicast message, where that message is sent to a specific group of recipients. And you can have a broadcast message, where you can send that message to all nodes or all devices on the same network. On an Ethernet broadcast, that would go to all the Ethernet nodes on that network. On a local IP broadcast, that would go to all the nodes. Now, if you do a global IP broadcast, that would go to all the nodes on the network. The main thing with multicast and broadcast is be careful with those, because those can take up a lot of network bandwidth and can cause problems if they're not handled properly. What network types are there? Well, there's LANs, or local area networks. That would be like a single building or a single area in a building. There's WANs, or wide area networks, where you'd have multiple areas in a building or multiple buildings and sites included. And then there's MANs, or metropolitan area networks, where it's a town or city-based network. The main thing you need to remember if you go between these different types of networks or different network sections is we have to use a function called routing. You remember we had the router, which was at layer 3. So let's talk about routing and subnets. So if we want to connect, let's say, these different networks, we've got network A, our corporation, connected to a couple of factories in Tennessee and Arizona. And those are all using different network identifications. Then we have to make sure to use a router to go between those networks. And that's what the router does. It translates between the different IP addresses and figures out where the message needs to go based upon the network ID. And again, that's a layer 3 function. Now, there's also a function with Ethernet and with the IP address called a subnet mask you may have heard of. It's a subnet mask. And with that mask, we can now create what's called subnets. Let's say we have this floor in a building. We have the accounting department and the tech support department. And of course, the accounting department doesn't want to allow the tech support guys to get into their systems, so they've talked to the IT staff and said, hey, we want to make sure we're isolated from them. And the tech support doesn't want the accounting guys getting over to their systems and so on. So the IT guy has a little bit of a conundrum until he realizes he can use a subnet mask. And once he realizes he can do that, he can now subnet the two systems. So he can create a subnet A, put the accounting department on subnet A, and then he can create a subnet B and put the tech support department on subnet B. Now, if they want to talk now between the two subnets, the IT administrator now has the ability to have them go through a router. So to go between the two subnets, they have to then use a router, and the IT administrator can determine who has access between those two networks again. So a lot of times you might have a different subnets in your facility, or you might want to put, depends on how you want to group the systems together. It allows you another way to group the systems in a layout like that. Okay, let's talk about network topologies a little bit. And because we know that Ethernet networks in the industrial environment are a little bit different again. A lot of times in an office environment, in a building, you're going to be talking about having a fixed installation. And a lot of times you're talking about a star structure or a tree structure where everything's coming back to a single point or a single maybe IT room where all the switches are in that room. In the manufacturing environment or in the industrial plant, a lot of times you might have a machine, and inside of the machine you might have, let's say, a linear structure maybe, or a line structure in that machine, because you don't want to bring each device in that machine back to a central location. It doesn't make sense in that case in the machine, so you can daisy chain, for instance, from device to device in that machine, and you might even be able to run a ring or a redundant type structure in that machine if it was an important or critical part of your process, for instance. Now, of course, we can also still use stars in the plant environment. And here's, again, an overview of the topologies. We have tree, star, line, or ring. Tree and star topologies, of course, give you easy administration of the network, flexible addition and removal of the stations. But again, you have a lot more cabling and a lot more maybe drop points where you've got to put cable or run cable in those instances. Line topologies are nice if you want to minimize the cabling overhead. And then in that case, you also might even have a lot of times the devices on the industrial side, especially like with Profinet, for instance, come with embedded switches in the devices. So you don't have to have an external switch in that case. It's optional. And then it allows you to do a topology like in a classic field bus system. So if your machine layout was laid out that way, you could actually just daisy chain from the PLC through each device on the network, and then maybe even have an engineering PC down here and connect it that way. And in that case, you would save not only on the cabling cost, but also you would have the switches already built into the devices. Another option for systems where you would need high availability or you have a critical process is a ring topology. Normally, rings are not allowed on a standard Ethernet. So if you tried to do that on a regular Ethernet and plug cables in a ring, you would cause a problem. What you need to have is switches that understand how to configure the ring, and then you purchase the switches. Again, it would be managed switches that would allow you to set up a redundancy concept. And then in that case, if you had a device, let's say down here working, and it failed, then the redundant ring would figure that out and make it go the other direction to send the data still to the device. And it would keep the rest of the system active if there was maybe a problem, a cable cut here or one of the switches went out. Okay, let's talk a little bit about network addressing and naming. Okay, network addressing. All computers or devices need an address to send and receive a packet, like an IP packet, or a data frame over Ethernet. So in your device or your PC, you've usually got the network adapter. It's either a card or it's built into your motherboard, the interface. And that interface has a unique physical address, which is programmed at the factory. Again, it's a MAC address. That's a 6-byte address. It's in hex. It looks similar to that. It's called media access control. And all devices on the network, of course, have to have a unique MAC address or you will have problems. There's actually some devices out there that let you set the MAC address. So if you have those types of devices, you, of course, need to make sure to set unique addresses. And the MAC address sits, again, at layers 1 and 2, the Ethernet and layer, network access layer. And then the IP address sits, of course, again, at the Internet layer. So if you want to use Ethernet and the IP functions, you have to have both addresses in your device. So you also have to have an Internet protocol address or IP address. And that's, again, typically on the factory floor, it's going to be a 32-bit address, the standard size. And this allows us to, again, deliver data if we want to use the routing functionality or if we want to use other protocols to manage the system, we can use IP for that. Another function, and of course these guys look a little bit confused in the picture there. The reason they look confused is they didn't use DHCP. So DHCP or RFC 2131, it's a way to have your computer automatically receive the TCP/IP configuration settings. So when you plug your computer into your office, normally I think most of us are probably aware of this, our computer automatically will pick up the IP address, and then not only will it pick up the IP address, but it'll pick up the subnet mask or the subnet we're on. It'll also configure the DNS servers and so on our computer. And it's a way for us to automatically receive settings. Of course, this is not always the optimum way to do it if we're doing it out of the factory. Most of the time in the factory, we would probably want to look at doing more of a static type of setting because this can always change, or maybe it's relying on a server, an IP server, so we need to think about that. Okay, now when we're talking about all these addresses, oftentimes it's pretty hard to remember what all the addresses are that you're using on the network. And so they came up with a concept called naming. So we can assign, on the network, we can assign names to the computers and the devices on the network. And then we have an alphanumeric name, so we can probably remember that name easier than we can an IP address. And in the early days, again, of the Internet, they had a file on each computer called a host file. And that host file would have a list of all the hosts, or all the computers and devices on the network in there, and then it would have the IP address of each of those devices. And what would happen is it would consult the host file. So let's say we have this network. We have John, Sarah, and Mark here at the facility, and we have our computer, and we want to send some data to Sarah's PC. Well, we would go into our computer and put, let's send this data to Sarah's PC, and then it would go into the host file and do a lookup and say, well, who's Sarah? Where's Sarah at? Well, she's at IP address 122.87.15.9, so that's where we need to go. So we're going to send the data over there. So the host file naming basically give us a way to use names for the devices and computers on the network. And most of you probably realize that your computer does have a computer name, so there's going to be a lookup table in the network somewhere. Now this system kind of became outdated again, because you can imagine if you had 500 computers, you would always have to keep these host files maintained and up to date. So they came up with a new system called DNS, or Domain Name System. And so what they do then is we can have a server, and the server has a list of all the device names. And then if we want to do a lookup, let's say we want to go to www.google.com, we can go type that into our browser. When we do that, in the background, our computer goes up to the DNS server and says, okay, where's the IP address of that website? Or where's the IP address of that computer we're trying to go to? And that is what allows us to be able to use the naming concept. And now we can, again, take advantage of that naming concept, and we can use naming with our devices. If your network, your factory network allows you to do that, you can take advantage of the naming concept, and you can have all of your devices named, and then you can put those in the list on the server, and you could then access the device by its device name even. And that's known as a DNS server. And with those devices, we would use, for instance, a fully qualified domain name is what it's called, or an FQDN. And with that, I think we've probably learned a lot today, and we've covered quite a bit probably in the short amount of time we've had. But we wanted to make sure everyone got a good overview and basics, overview of Ethernet and networking basics. So when we see you at our next Profinet seminar, you'll have a lot of this already behind you. I think it's a good base to start with. And so hopefully we were able to cover the Ethernet what and why, how the OSI model applied, the standards, and then the differences between Ethernet and industrial Ethernet, and then the basics. And of course, if you have any questions, we'll be glad to answer those questions. Carl, back over to you.
Okay, Hunter, thank you very much. Wanted to remind everybody that we have a lot of additional resources available to you. While I'm going over these, feel free to enter any additional questions that you may have in the question frame. First of all, of course, the website. We would urge you to go to us.profinet.com, pictured down here. You find a lot of additional information there. We have a number of newsletters that you can subscribe to. When this webinar is archived up on the website, you will also find a PDF of these slides, and all of these links here will be live. So these will take you to these various newsletters, to the Profi blog. We have a forum specifically devoted to Profinet, which also occasionally gets into some industrial Ethernet types of questions. There are a number of books of there are a number of books available. You can click on that. We have some additional webinars that give you more detail, and some of the questions that we've had come in, I'm going to refer you to some of those. We offer a series of free one-day training classes around North America. Happy to have you attend one of those for us. We also offer in Johnson City, Tennessee, a full-week certification class in Profinet. It does cover a lot of the industrial Ethernet basics as well before getting into the details of Profinet. As I mentioned, PTO is a member-supported organization. We certainly invite you to join PTO. Lots of benefits accrue to you as a user, distributor, systems integrator, or manufacturer of automation devices. Okay, with that, let's move over to the the questions. Remember, you can enter your question in the question frame that's on the right-hand side of your screen. If you're watching the archive version of this, you can email your question to webinarq@ptoregistrations.com. So I'm going to give Hunter a break here and answer these first couple of questions myself. One of the questions was, why would I move from Profibus to Industrial Ethernet? I already have Profibus in the facility. There are a number of good reasons to move from Profibus if the need exists. And typically those needs might be the need for increased bandwidth. Perhaps you have some vision systems that need to be brought onto the architecture as well. If you need address space, you have a lot bigger address space available in something like Profinet. Because of Industrial Ethernet building on standard Ethernet, you can also use wireless connectivity, and that's really a good benefit in lots of different kinds of applications. We do have a webinar specifically devoted to wireless, so I urge you to take a look at that. Another benefit is diagnostics. We didn't really go into those today because we do have another webinar that covers diagnostics, specifically that come from the Ethernet capabilities from the office world that we can use in the industrial world as well. Another one of the general questions, and I'm going to set the tone for this one and then pass it on to Hunter. Someone asked if there is a limit to the length of Ethernet cable, and that reminds me to point out to you that we've been mostly talking about copper connections here. Ethernet can also be connected wirelessly, as I've mentioned, and using fiber. So there are many choices in the medium that you can use to convey Ethernet frames. Hunter, do you want to address the length question?
Well, the length question on copper, I can answer, is typically, depending again on your device, but typically it's going to be 100 meters on a copper connection that you can go from switch to switch or device to device. And then, of course, you can go from that switch then another 100 meters, so you can, again, daisy chain from switch to switch, but the max distance typically is going to be 100 meters on that. With fiber, it depends, again, on your fiber components, but a lot of times you're talking like 2 kilometers, maybe even 10 kilometers you can go, depending on what type of fiber you're using. So you can really go some pretty great distances with Ethernet. And that's one of the other advantages, I think, from the other field bus systems. With a lot of the other field bus systems, you were pretty limited on the distance you could go without having maybe another repeater device or some other device to extend the distance, whereas with switches, you can go 100 meters from each, basically on each leg from that switch, for instance, you can go 100 meters. So you can cover a lot of distance if it's copper, for instance.
Okay, thanks, Hunter. We have a couple of Ethernet switch questions now. Hunter had talked both about managed and unmanaged switches, and someone was wondering if we have a recommendation there. I've often heard it said that you will use a managed switch or wish you had, and I think the reason for that is the diagnostic capabilities available in a managed switch. You can actually get information on what the current status of things connected to the switch are. In addition, you can actually kind of get some preventative information. If you can see that one port of the switch is getting a lot of retries, for example, you may want to go out and check the physical cabling that's connected to that. Managed switches are obviously more expensive, but if downtime is even more expensive to you, then that's more of a reason to use a managed switch. Certainly there are occasions where you might want to use an unmanaged switch, but again, keep in mind that the diagnostic capabilities are not going to be there. Okay, another question was, I have heard that switches need to support IGMP snooping. What is that, and do I need it? Hunter, do you want to take that one?
I can. If you have a protocol which supports, which does a lot of multicasting, you remember we talked about the different types of messages. We had unicast messages, multicast messages, and broadcast. Well, if you have a protocol or a network protocol that uses a lot of multicasting, if you don't have IGMP, that multicast basically acts like a broadcast, so it basically floods all the network nodes. So IGMP is a way you can actually use a multicast protocol, and IGMP allows you to create what's called multicast groups. So you can group what recipients are going to receive that multicast message. That's what IGMP helps you do. And you usually have to have special switches, maybe some special configuration options in your switch to be able to set that up.
Okay, and just for the record here, Profinet does not need to have that capability in the switch. Okay, looks like that is all of the questions that we have. I do want to ask if you've, once the session concludes here, a survey is going to appear for you. We definitely would appreciate it if you would take some time to complete that survey. Let us know what you found out today that you needed to know, if there was something perhaps missing, and give us some suggestions for future webinars. I do want to reinforce that we tried to cover today really more of the generic Ethernet capabilities. We have additional webinars available specifically for Profinet, specifically for wireless, and specifically for diagnostics on industrial Ethernet. So with that, thanks everyone for attending today, and we'll catch you at the next webinar.